Greetings, I'm Yvonne, staff for Science for the Public, and I welcome you to Contemporary Science Issues and Innovations. One of the most urgent issues currently is how to deal with greenhouse gases like CO2 and methane. Methane is released by farming, it's mining, fossil fuel drilling, and by melting permafrost, and it's hard to control. A potential solution that is attracting considerable interest has been developed by the Desiree Plata lab at MIT. Desiree Plata is the Gilbert W. Winslow Career Development Professor in Civil Engineering and Associate Professor of Civil and Environmental Engineering at MIT, and she's received many awards for her work in green engineering, and the methane capture innovation may bring her yet another one. In this discussion, Dr. Plata explains the serious issue of methane emissions and her team's ingenious solution, the use of zeolite clays, which are abundant and inexpensive. Though this innovation is still in development, it's receiving a lot of attention. We are pleased to welcome Dr. Desiree Plata. Welcome. Thank you for joining us today. And I'd like to ask to start with, if you would please explain the methane issue. So we know there's the CO2 problem and there's a methane problem in terms of the greenhouse gases. Could you give us a little background on that?
Sure. There's two really dominant greenhouse gases that are accumulating in the atmosphere. One of them is carbon dioxide, and most people have heard of that. Another one is another small gaseous molecule called methane. It's got one carbon atom in the center and 4 hydrogen atoms distributed around it. In the next 10 years, methane will cause as much climatic forcing or radiative forcing or warming as CO2 will. We're not typically used to hearing about that because we tend to look over 100-year time horizons. And if you look over those longer time scales, methane appears to do about a quarter of the warming as CO2. And so this is why it really hasn't been at top of mind for people, because we tend to focus on these longer time scales. But if we think, what could we do today to change the rates of warming in our lifetime? Acting on methane, a near-term warmer, is one of the biggest levers that we have to change global warming rates now.
Because that's like 80% of the heat or something. Is that the case, or that's the hot stuff?
It does a lot. Yeah, that's right. And so if I could, spend a little time talking about the chemistry, the reason that greenhouse gases behave like greenhouse gases is because of the way that the molecules move. And so carbon dioxide and methane both have vibrational and rotational modes. I like to say to my students, they got the dance moves going. And the energetic transition of those modes overlaps with outgoing energy that's trying to leave the Earth's surface. And so methane, it turns out, is really good at absorbing that energy and re-emitting it back to the Earth's surface. And a lot of that re-emission happens as heat. And so that's how greenhouse gases work. And it turns out that methane's potency can be up to 120 times that of CO2. And so it has this real powerful absorptive effect that ends up causing this radiative forcing or global warming effect. One of the key differences between methane and CO2 is that methane is relatively short-lived in the atmosphere, and so that's why you see the power of the warming effect decrease over time, because those molecules are going to start to turn into CO2 through natural processes. So molecule for molecule or pound for pound, methane's always doing more damage than CO2. It's just that it front loads that damage. It happens really quickly.
And it seems like now everybody is agreed, you gotta get it out of the atmosphere somehow, because we can't keep this up. And it comes from multiple sources, correct?
Yeah, that's absolutely right. And that's one of the things that makes methane management so hard.
Yeah.
When we think about CO2, we think about coal-fired power plants, natural gas-fired power plants, point source emissions, industrial manufacture, where we might be combusting fossil fuels and generating CO2 directly. And the handy thing about that is that you've got concentrated sources of CO2 that you could potentially pull out. And we have good technologies to do that. Some of them are not cost competitive, of course. But methane kind of comes from everywhere.
Yeah.
It comes from forest fires. It comes from the breath of ruminant animals, so cows and sheep that we cultivate for meat and dairy. It comes from fossil energy extraction as well and natural gas distribution. But it also comes from natural sources like wetlands and permafrost. And it's kind of
coming out now.
Yeah, seeping out at these low levels all over the surface of the earth. And I like to say, any self-respecting engineer runs in the other direction when they hear that the thing you have to take out of the atmosphere is a dilute reactant. That's a challenge. And
right, evidently. So I appreciate that, because it seems as though it's very diverse. The sources are very diverse, and they're a little hard to manage. So just recently in the past week, there's been a good bit of news about the peatlands and Siberia and so on. And this, that's really tough. This is really going to be tough. So
yeah, that's right. I mean, the sources are what we would call spatially and temporally transient. So they're coming up in different spots and at different times. And you can imagine, almost like a game of whack-a-mole. And if you've got to stand up a technology to address that, it's really hard to move that around or know where to put it in the first place. And so you're absolutely right. There's global agreement that we need to cut methane emissions or take methane out of the atmosphere.
And maybe both.
And maybe both, yeah. And to the tune of about 45%, hopefully within the next 10 years. And if we can do that, we could actually save a half a degree warming by mid-century.
That's incredible.
That's dramatic,
That's incredible. That's a little bit cheering to hear that for a change. So there's that. It's just that this is evidently very challenging. Now, you have a way in your lab. You've come up with this very clever system, I guess, but it's getting a good bit of attention, and it appears to be that it potentially is very effective and inexpensive. Could you tell us all about it?
Sure. Yeah. So we actually, so my training, I'm an oceanographer by training, a geochemist. So I study the way carbonaceous molecules change form. And I like to take inspiration from nature. And it turns out that there are organisms called methanotrophs, or methane lovers, that generate energy and biomass from methane. And they do it at relatively low temperatures, and they do it in the presence of oxygen. And that is exactly what we need, something that can convert methane to not methane at relatively low temperatures and in the presence of air, of course. So I dug into the literature a bit and looked historically at what people were using to mimic that biological process. And there were two big classes of materials. One of them are clay aluminosilicates. So they're clay particles that you can dope or add metals to. And there's something special about the addition of that metal into the pore spaces in the clay that helps it hold on to methane and bring it into contact with an oxygen atom or an oxygen molecule from the air and convert that methane into something else, typically CO2 or other products. And so this work had been going on for many years in industrial application space, so very concentrated methane, high temperatures.
Yes.
And so we tried to say, well, can we get this to work in more relevant conditions that you would need it to take methane out of the air?
Right. Now, you're using, the metal you're using is copper. Is that correct?
That's right.
So you're right on top of that. So copper and zeolite?
Zeolite, that's right.
This ordinary clay type?
It's functionally an ordinary clay. So
cat litter.
Yes.
Right.
And I have to give my students credit there for recognizing that one of the most common uses in industrial applications that most people would be familiar with of aluminosilicate clays is cat litter, in fact. So it's a very common material that is used in lots of different different applications. It's one of the most abundant materials on the surface of the earth, the clay aluminosilicate materials. And so the good news about that is, it's cheap. It's very, very cheap. And so that can make the technology very cost competitive. Copper, of course, is a commodity chemical. The price fluctuates, but it's relatively cheap compared to things like platinum and palladium, which we typically use for these chemistries.
Right. So you put this together and it absorbs the methane and converts it to something. Well, I'll get you to tell us.
Yeah, no, you got it. You got it right. Yeah, it interacts with the methane. And one of the tricky things about methane conversion historically is that carbon-hydrogen bond is very, very strong. So methane's the main component of natural gas. We get a lot of energy out of natural gas because of those carbon-hydrogen bonds being so strong. And so doing that first process of removing that hydrogen atom, that's the hard chemistry. And that's what these zeolites, these clay aluminosilicate materials do for us. So there's the copper that's constrained in the pore space that can grab onto a methane molecule and bring it into contact with an oxygen atom in the right geometry to promote the removal of those hydrogen atoms and start to turn that carbon that was methane into a CO2 molecule or something similar.
And before we get into how that system is structured, I want to just ask one more thing. I think that I read that these other the technologies for this methane removal, one of the problems is they have to use high heat, and that's the last thing you want to do around methane. I think that you have pointed that out, but your system gets around that. Is that correct? It's not low temperature, but nothing like the high temperatures.
That's right. So people have been looking at this problem historically and using things that are regenerative thermal oxidative processes that use, yes, I know, high heat. So you can, it's high heat, but that word regenerative means you're switching between your methane source and a pure oxygen source. And you're doing it, yipe, exactly. And so pure oxygen goes, goes boom. And so you've got potentially flammable streams of methane. So once methane gets above about 4%, that's the ignition threshold. And once you're above, I think, around 515 degrees C, you can have an auto ignition process for methane.
Whoa.
So that means you can have an explosion.
Absolutely.
That's of course very dangerous if you're a coal miner or
that's
right, or a gas worker. And we've had natural gas explosions, of course, in this region of the United States and elsewhere. So it's not as uncommon as we would like, these auto ignition problems.
Right.
And so that's one challenge, is the temperature. So once you get up above that 515 degrees C or so, you can instantaneously ignite methane in the presence of oxygen. So if you built a technology that has to run at 600 C or 1,000 degrees C, you're sunk.
That's right.
And then the second problem is this reliance on pure oxygen to regenerate the catalytic systems that we've had before, or the processes we've had before. And pure oxygen itself creates a secondary explosion hazard, a need for another gas, a compressed gas on site. And so if you can run in air all of a sudden, that makes things a lot easier. And so that was one of our key recognition points. We said, if you don't need 100% oxygen, there's no real reason. The air's 20% oxygen as it is. And so we tested that systematically and showed you can make this chemistry proceed in air.
So it sounds like a big leap. It has many advantages. Now, how does it work? If I've got a coal mine or a fuel industry or the peat, whatever, I take it you have to specialize the system for those kinds of things. But any example will do. How does it work?
Yeah,
do I put a cup of it there?
Well, it turns out that it would work in many different applications, but we kind of want to go where we're going to get the most bang for our buck. We have a, climate emergency is how a lot of people phrase it. And so we want to be able to deploy these systems in a way that's going to bring a net greenhouse gas benefit. So we don't want to be burning more electricity, greenhouse gas equivalents than we're saving. And we want to have a quick or rapid impact. And so we want to go to places where the methane is not super, super dilute, but where it's slightly enriched. And so the places you might go to are places like dairy barns or meat barns or coal mines. And so those two applications are what we're really focused on right now. And so at coal mines, you get enrichments of methane that can be up to 4% methane, but are typically lower, between 0.5% and 2% methane concentrations. So quite concentrated. And the other thing about mining applications is you're moving a lot of air, and you do that for the miner's safety. And so these large volumes end up translating into very large global methane emissions. And so if you could have a technology that can treat those large volumes of air and take the methane out functionally by converting it to something else, then you could have a big impact on atmospheric accumulation of methane. And then natural processes will take over to start to draw down methane in the air. The other place we're looking is at dairy barns. And in large agriculture, what I call industrial agriculture, you see these cross-ventilated barns. And so if you have a long barn, there are fans on one side pulling in fresh air and then putting out the air that would normally have accumulated methane. So you do this so the cows can breathe, so methane doesn't accumulate, for temperature regulation. And those fans are actually really nicely designed such that we could just clip a filter, if you will, or a catalytic converter type of thing on the outside of those fans. They're big fans. I'm pantomiming something small, but it's more like this. And so if you could develop those two applications, you really could potentially start to see methane accumulation in the atmosphere go in the other direction.
I see. That's interesting. I would like to just mention that I don't know if people are familiar with industrial meat production, the cattle and that sort of thing, and they are very confined, and there are zillions of them, and as you say, they're in these barns, they're all squeezed together. If they were out in pasture, but and maybe the problem isn't as great if there are not so many. In this situation, they are packed and there are thousands, correct? So if they are packed, then the system will work.
Well, it could potentially work even if they are, say, free range. So grazing
that's
around.
Interesting.
Yes, it's not as effective. Of course, you're going to have fugitive emissions of methane at that point. But we're going into the field, this summer, hopefully, to test this at an actual large-scale dairy barn. And so we will test it in the indoor environment, but also in the pasture environment. And so you have to have some understanding of, how the wind is moving on site and how quickly and how much of that wind you could potentially capture. And of course, your efficiencies are going to be lower if you're trying this open air abatement technique because their methane's going to move away. But if the cows are inside in these barns, then you would be able to potentially access almost all of the methane that they're during those indoor times of day. I mean, one thing I've heard from some, dairy and meat industry folks is that with climate change, they are concerned they will have to move to progressively more indoor environments in order to protect the animals from the extreme weather events and heat in particular.
The other one is like oil and gas drilling, and just recently they've been observing from or measuring from aerial measurement, which they're finding there's a lot of methane that they've missed before. Can your system handle that?
Yes. Okay. So can the system handle that? I will say that it could, but there are probably better strategies for managing those emissions of methane.
That's good to know.
Specifically, I would say that if you have a good sensing platform where there's a methane leak, you can go and turn that off in many of those cases at the well collection sites, the wellheads in the distribution system, and that is often going to be the best strategy. Just find and fix the leak. The trick is being able to do it quickly enough. So what people are finding in these aerial sensing efforts is that these super emitters or large bursts of methane are transient in time. And so you might miss them if you're not looking for them, or if you're trying to observe by satellite, you might not get the information in the amount of time you need to go and respond to the leak. And so some hybrid of ground-based sensing is thought to be needed, and interfacing that ground-based sensing with controls that would allow someone to shut off those leaks is going to be very important. The other strategy that you see used at highly concentrated sources of methane, like at these wellheads, is flaring. And so the idea is to just light the stream on fire. And our technology is really better for applications where you can't do that. So once you get below that 4% concentration threshold, you really can't light the methane on fire. It's the same chemistry you're driving, methane to CO2. It's still exothermic, but you're doing it catalytically at this very small scale or trace scale.
I see. So far, you can manage, like you could set up around mines, coal mines, things like that. The fossil fuel stuff is a little more complicated. I mean, into the oil and gas drilling, that's more out of reach, maybe.
It's just not the smartest thing to do there. There's something cheaper to do and more effective.
Okay,
so.
that's important.
Yes.
How about the melting peatlands, that kind of problem?
Yeah, peatlands and wetlands are a big concern for people. Yeah, and we don't know, I think, is the answer. So one of the extreme calculations we did at first was, well, what if we just put this on every air handler on the face of the earth? So on the top of any big building or in people's homes, we're moving air constantly in the built environment. So what about deploying this catalyst there and just treating that air as it moves? And it turns out that process would be a little too slow, because the methane the air that we're breathing contains about 1.8 parts per million methane. That's quite a dilute concentration.
Yeah.
The technology works there. You could do it. It's just not going to give you that fast impact that you want to see, that standing this up at coal mines and dairy barns would do, or other similarly enriched sources. Now, permafrost and wetlands, peatlands in particular, those do give off relatively enriched methane bursts, if you will, but they get diluted to atmospheric concentrations fairly quickly. And so it's a big question about when you would deploy them, how often you need to be running them on site. Is it worth your while to be there, or should we really focus on these more concentrated sources where you can have a bigger impact? I will say about the peatlands and the wetlands, because for the viewers' benefit, those are natural sources, but they're sources that are accelerated by human behavior and climatic change.
Yes, and so they're melting.
That's right. As we warm the earth, permafrost are going to give off more methane. That problem is probably not as big as you've heard. Wetlands, on the other hand, are an enormous source of methane, and our changes in the way that we manage land have led to big increases in atmospheric methane concentrations. And so the big increase, methane's got its own hockey stick right now going on, just like the CO2 accumulation. It's thought that big increase is actually not necessarily attributed to oil and gas, but the way that we have slashed and burned wetlands in Southeast Asia. And we've done this in order to establish other industries like palm oil production.
Big one.
Yeah, and for the people that live there, that is something that's going to contribute to their socioeconomic ability to thrive and prosper. But for the climate, it's quite bad, because you get one huge release of methane all at once. So what is the solution in those cases? Our technology that we've developed, yes, it could work. I don't know if it provides an economic benefit that would incentivize its use there. I don't know if we're too late to actually solve that problem. But what I do know is that we need to get on the ground in those regions and ask the people who are responsible for those practices, what would it take to change their behavioral patterns? What could potentially motivate you to stop these slash and burn practices of wetlands and peatlands? And how do we preserve our current wetlands in a way that will reduce the natural emissions of methane from those systems?
Right. destroying the rainforest in Brazil a lot now too. It will, and I'm sure that is causing this problem. Is that true? The methane problem also, does that cause one? And if so, can you address that?
Yeah, I would say that is we can learn something from what's going on in Brazil. Right. So I'm about 40 years old, and I have been hearing about the destruction of the Amazon my whole life, and kept an ear to the ground on the problem. And I think one of the things that you've seen is it's very hard to motivate the preservation of those forests. And even when you incentivize it, the economic benefits of destroying those forests are so great to the local population, maybe not the indigenous populations, but other locals, that these practices still happen. And then, of course, there are accidental fires that can contribute to the destruction of those forests. What goes on in the Amazon and in those forests, I think we have a lot to learn in terms of our land use practice management, but it's not exactly the same biogeochemistry that's going on. So you're mobilizing carbon in a different way. It's not necessarily contributing to large methane releases, and it's not necessarily contributing to a loss of carbon uptake potential that we tend to think about. Trees have this beautiful ability to be able to fix carbon from the atmosphere, which is exactly what we're trying to simulate in the lab, CO2, of course, but the Amazon may be playing a smaller role there than, say, our northern boreal forests are.
Very interesting.
Yeah, so I think the socioeconomic learnings, though, from the example of the Amazon are very poignant and should be applied as we start to think about ways to incentivize preservation of wetlands more strategically.
Right. One more thing I would like to get very, very clear. You have pointed out that people do freak out when you say in using this system, it converts to CO2. And people go, oh my gosh, right. But you've said, hold on, tell us why.
Yeah, so I know that we have done a great job helping people understand that CO2 is an important greenhouse gas that we should care about. But here's the thing. If I take half of the atmosphere's methane and I convert it into CO2, I've taken atmospheric CO2 from 415 parts per million CO2 to 416 parts per million CO2. It is a minuscule contribution to atmospheric CO2 levels, and the net impact to warming reduction is almost 16% of warming saved. That is a big deal, and it's something that we need now.
Okay, so the CO2 lasts thousands of years, but the methane doesn't last as long, but it holds the heat. That's the thing. Is that the idea? And that's what you've got to get rid of.
Kind of the idea, right? And so all our technology is doing is accelerating the natural fate of methane in the atmosphere. So when a methane molecule is released to the atmosphere, in about 10 to 12 years' time, it is going to become CO2. It's going to do that with a natural atmospheric reaction. We're trying to speed up that transition because CO2 is the much more benign molecule. And so we're saying get it out of this really strongly warming form and get it into a much more benign form, the CO2, quickly. And because there's not a lot of methane in the atmosphere, it's okay. It actually just is a very small fraction of the CO2. So you don't get a big increase in CO2, but you get a big savings in warming potential or radiative forcing.
Now, sooner or later, we're going to have to get that CO2 out, too, because we have too much of that. Are you working on it? Or the follow-up?
That's a good point. I mean, you don't actually have to get it out because it is such a very, very small contribution on the backbone of what we already do as a species. And so the Earth is processing that CO2 on its own. And again, just to reiterate, methane's much more dilute in the atmosphere. It's 1.8 parts per million by volume, whereas CO2 is much more concentrated, and those cycles are enormous, on the order of gigatons, and methane cycles are much smaller relative to that, but they have this disproportionate warming effect. So your question was, do we have to get CO2 out of the atmosphere? There are technologies that are able to do that. There are direct air capture technologies. There are point source carbon sequestration technologies.
Conversion, all kinds of stuff, right?
Yeah. The problem with the direct air capture technologies, which is kind of the analog of our methane capture work, is that they're extremely expensive. And so they would never pay for themselves. They would have to be a philanthropic investment unless you converted them to something that has a very high, market potential. Taking CO2, for example, to something like ethanol, or which we need to sanitize our hands in a pandemic, or consume as vodka, right? Which you can sell for.
That'll market.
Yeah, that will market. That exists today. There's actually a company that does that commercially, and so you can get ethanol that's been captured from the air.
It makes you feel better all over.
Makes you feel better all over. That's right. So those technologies exist, I would say, and probably don't need as much development imminently as these near-term warming technologies do.
Okay. Now, the CO2 capture and conversion, capture, storage, all of that, a lot of those don't scale. You pointed out the expense and the difficulty, the technical difficulty with a lot of those, but they also don't scale well, like you need something big. How about your zeolite, copper zeolite system?
Yeah, so full disclosure, we're still working on the perfect ratio, but it seems like we can get the scaling to work, at least on pen and paper or in a computer space. So our early calculations indicate that we should be able to scale these technologies in a meaningful way at the number of sites they would need to be present at, and at a competitive cost.
Right. You pointed out that you are going to try it out, like in the barns and things like that this summer, that you're going to test in the field, in other words, this summer. I'd like for viewers to know this kind of system, that people have to go back and forth, redesign, do this kind of stuff. Could you tell us a little bit about that? So you take your system out there and then what?
So what we'll do this summer is very basic. So instead of having the cool thing that you snap on to the outside of one of these cross ventilation fans, we'll just go with a very basic system. So a smaller micronized reactor, maybe the size of this
litter
water
pan.
bill. Yeah, a litter pan, if you will.
A copper litter pan.
And some fans and some heating units, and basically look at the methane coming in and the methane going out, and then run back to the lab and figure out, okay, what frustrated this process? What were some of the challenges that we ran into? We're also developing the coal mining application. We've got a recent investment from the United States government to help us develop reactors and test those in the field at coal mines. And we've got some very gracious coal mining partners who are letting us test a scaled down version of the reactor, where we'll try to learn, what poisons this catalyst. Is it possible that water vapor in the air causes problems, or other chemicals that you might encounter on site, and how long can the catalyst last out in the field when it's doing its job?
Right, I see. Now, your lab does a lot of interesting things. This, in a way, maintains or sustains these fossil fuel industries and things like that, which could be a problem as well, because it's clear there's a great urge to get rid of coal mining. That's going to be the solution, get rid of these fossil fuel things. Are you developing other things in this very interesting lab that is going to be used in environmentally friendly technologies? Yeah,
so I'll say, first that the mission of the work that goes on in my lab is to change the way that we invent materials and processes. Since the Industrial Revolution, our approach to innovation has been to invent, use, wait to identify a problem, and then respond to that problem. And so environmental engineers of today spend a lot of time chasing our tails on old contaminants. And we would much prefer to use the knowledge that we have about the Earth system that we've developed over the last 100 years and predict what those problems are going to be and build a better system from the start. And that's very analogous to green chemistry, green engineering, but sustainable design, really, of all industrial processes and practices. That said, we are stuck with fossil fuels for a while. And I know that people are under the impression that this is a question of political will. It really isn't. Even if we kind of do our best, the estimates in the United States are that we're going to need natural gas at least through 2030. And so I like to say these are inevitabilities. If hydraulic fracturing is going to be here, if we are extracting natural gas, I want my lab to be part of the solutions to making sure that people and the Earth system and ecosystems aren't made sick by that industrial practice. And we can do something about that now in our time instead of focusing on a very distant future. That said, my group is also working to enable renewable energies. I have a startup company that's actually scaled a technology that reduces the CO2 footprint of metals recovery.
Oh, yeah.
Yeah, so we can circumvent mining and we can start to enable energy storage technologies that are needed for renewable fuel. So we do try to strive for very tractable inroads to get to that future that we all want to see. But the reality is that we have needs that we can't meet today without fossil fuels. And if fossil fuels are here, I want to make sure that I'm doing everything I can to protect the Earth, its people, and its animals and plants.
And in terms of, this is a new innovation, has to be tested and all like that and refined. How long do you think until you can get something that is at scale that can be deployed?
Yeah, so conservatively, I should say it'll take about 10 years. But I will tell you that the nice thing about this technology is we don't have to build anything new for it to exist. We kind of have all the pieces that we need, and we just need to get those pieces together in the right configuration. And so if we had all the world's resources and testing capacity, maybe you could do it in 3 years or so. But the truth is that it'll probably take a bit longer to do that. Yeah.
Right.
But there's no big outstanding hurdle that needs to be overcome that we can't see a clear path in a current off-the-shelf technology to do.
Right. I hope this takes off. I wish you all the best in this. You're doing a lot of other things. Is there anything else going on in this interesting lab that...
Oh, yeah. So much.
Yes, because I get an idea for viewers that you have postdocs and graduate students and stuff, and they're working on a lot of different things. But do you have any other projects that you...
There are lots and lots of projects that I would be excited to tell people about. But one of the things that I want to take some time to take advantage of this opportunity is to help people realize that, I, in my lifetime, have seen a major transition in the interest of industries and corporations in incorporating sustainable practices into the design of their technologies. And that gives me great hope. I also think that for young people who are trying to decide how can I use my talents or my interests to affect change in this problem, there is a way for everyone to connect. So what I like to tell my students is find something you love, whether it's journalism or chemistry or engineering, and pair that to a thing that you care a lot about. And then you would be motivated and able to impact a real change. We're at a very unique point in history where all of the right forces are coming together to move us in the right direction. So I know what you hear on the news every day is incredibly depressing and anxiety-inducing, especially for young people, but there is a lot of hope, and we need people's talents on these problems.
I appreciate your saying that, because it comes at the right time. It's true, people do feel defeated in many respects, so we need your lab, evidently, and your goodwill. I really hope this will take off. I'm sure that we're going to hear more about this coming up. It's already, I've put it on your event page, the article in Wired, and there's another one. I want to say Grist, but that's not it. But you're getting some press, and I hope that there'll be good coverage, and I wish you the very best on this.
Thank you. Thanks for helping us get the word out.
Thank you for being with us today, and good luck.
Thanks, Yvonne.